You know these chemicals. Okay. Then we're missing something. Is that right? Sometimes, for glyceraldehyde 3-phosphates, they have a transition step. They could become dihydroxyacetone phosphates. That's a transition stage. So this is the procedure. You know the name, you know the chemicals. Okay, how many points you get? 1, 2, 3, 4, 5, 6. Multiple by 0.5, that's 3 points already. Okay, right here. 1, 2, 3, 4. So you get 5 points. Only you write the number there, or only you write the name. So we're going to talk. Glyceraldehyde 3-phosphates, what it looks like. Glyceraldehyde 3-phosphates. Okay, 1,3-biphosphogycerate. What it looks like. Something happens going to be there. Okay. So I do this way, this way. 3-phosphoglycerate. Phosphoglycerate. Move that. Pyruvate. Lose water. They don't like these things. This is very unstable when you see these. Okay, so what's that? Okay, pyruvate. If you don't know pyruvates, then you have a problem. Okay? You write a structure there. How about that guy? Okay, what is dihydroxyacetone? This is dihydroxyacetone. Then what is dihydroxyacetone phosphates? Take out of this guy. Become a phosphate. Okay, but this is a transition step, so we don't talk about this too much. Okay, what are these enzymes? Now, only a little bit complicated is on the top, but this is maybe we call it aldose. Is that right? This is glycerate kinase. Okay. What is right here? Phosphoglycerate kinase. How about here? Mutase. Okay, how about here? Analase. How about the last one? This is a pyruvate kinase. So easy. Everything is the same. Just the name. You look at the name, you know it. So it's just something extra. Okay, we wrote the name, we wrote the structure, what we care. How many ATPs we generate? Okay, this is going to be something tricky. Okay. Okay, you look at here. Glyceraldehyde 3-phosphates become 1,3-biphosphoglycerate. This is something dramatically will be happening. Is NAD plus will reduce to NADH and NADH2. Okay. This is going to be a key. What's the enzyme they need? Dehydrogenase. Okay? 1,3-biphosphoglycerate, it becomes 3-phosphoglycerate. What happened? ADP. Add the phosphates. Where does phosphates go? Goes to ADP. Then becomes what? ATP. Yes, correct. 3-phosphoglycerate become 2-phosphoglycerate. This is, you can understand it. It's like a mutase. What means a mutase? You go inside. It's just like change a little bit structure. Something like isomerization, nothing changed. Okay. Is this change too much? This lose more water, nothing happens. How about the phosphophenolpyruvates become pyruvates? Of course there's something happening, is that right? Yes. So right here is ADP and a phosphates becomes ATP. Okay, here is the thing. You read a textbook or you read something, whatever the class tells you, high advanced nutrition. They say glycolysis generates only 2 ATP, is that right? Yes. Okay. 2 lines. Okay, so 2 ATP right here. Right here, 2 lines. So 2 ATPs right here. Added up together equals 4 ATPs. And then during the investment area, we hydrolyze the 2. So the total is 2 minus 2 ATPs. Add 4 ATPs equals 2 ATPs. This is what the textbook tells you. But you should know. They think glycolysis is a single independent pathway. They did not think these things happen, which is NAD plus reduced to NADH2. They did not think this happened. Therefore, this 2 ATPs is not included. This NAD plus reduced to NADH2. Okay, if you are included there, how many? This is 3 ATPs multiplied by 2. That's 6 ATPs. So if you add up them together, 8 ATPs. Okay? And this is something which is a little bit confusing. So why, when you do aerobic respiration calculation, you think the final is 8 ATPs? But why we talk about glycolysis, they always tell you there's only 2 ATPs. Because they did not take into consideration of that guy. Okay? So let's forget about this moment. We mentioned that the fermentation generated 2 ATPs. Where it comes from? That comes from right here. Okay, not included on the top. Here is another thing I want to mention. You know bacteria, when they go through this process, they have a choice to go. They can go citric acid cycle, complete aerobic respiration, generate lots of energy. They could also go fermentation. But you know, some of the bacteria cannot go this way because there is no SOD and the catalyst. The toxic chemical will come out. They cannot come back in. So what they have to do? They have to go through fermentation. Now, fermentation generates energy is very low. It's only 2 ATPs, but they have to continue to do. So what they have to do? They have to be combined with glycolysis. A single independent glycolysis, the bacteria cannot survive because NAD reduced to NADH2. There is no empty well for them to accept electron, which means the electron carrier cannot recycle. Once glycolysis and the fermentation combine, they could be work together and the recycling of the NAD, so they can start working and survive all the time. Therefore, anaerobic bacteria starts to create it. So you need to know the story behind that. The fermentation and the glycolysis has to be coupled. The 2 ATPs coming from actually is the glycolysis. And of course, you know when NAD becomes NADH2, what this comes from? Electron transport chain. That's why they have 3 ATPs. Is that right? Okay, so this is end up we talk about glycolysis. Now this guy right here. Okay, then we split out here. All have enough space. We call citric acid cycle. Okay, so let's do it. Pyruvate. First of all, there's a transition step called acyl coenzyme A, or acyl coenzyme. Okay, now you're going to draw a circle. So what's going to be the circle going? First one, citric acid, or citrate. Some textbooks called citrate. Okay, and go here. Isocitrate or isocitric acids. Then go here. Alpha ketoglutarate. Then go here. That's succinyl-CoA. Then go very flat. That's succinate. Then go here. This is called fumarate. Then go on here is malate. Then all the way close. Oxaloacetate. Then go back. That's a circle. Okay. You know the name. I know you not have a problem. 80% of you know the name. How about the structure? Maybe difficult. And I tell you the way to write. It's easy. This pyruvate you know. Okay, you already know. If you don't know pyruvate, then you have a problem. I said you have to know. Okay, we don't care about all these things. Let's look at the citric acids. Do you know the structure of citric acids? That's a key. What is the structure of citric acids looks like? This you should know. Write on your notebook if you don't know. Practice lots of time. Because everything comes from here. How many carbon? 6 carbon. Very asymmetric. Okay, this is citric acid. That's why I draw in the lab. I want you to have some impression. Now, what is isocitric acid? Iso is always easy. Isomerization. This guy goes here. So, this is isocitric acids. CH2, COOH. Then go H right here. Then go down. We see OH, H, and COOH. Okay, alpha ketoglutarate. This guy is something magic. You know this guy can do other things. Majority of lots of the other pathways it could do. This is called metabolic precursor. Because they can go any other metabolic pathway, depends on the situation. So what it looks like, they definitely going to have something going to happen, dramatically happen. NAD reduced to NADH2 plus release carbon dioxide. Okay, which means something here going to come. Okay, therefore, what is the structure of this guy? CH2, CH2, C. Okay. Once you go here, you have these guys here. This is not going to become stable. This will be removed very soon. Become succinyl coenzyme A. So what is that? Okay, just easy. Okay, you know this guy. Do you know acyl-CoA? What is acyl-CoA? That's easy. Okay, then goes here. There's something happened. Okay, then goes here. Go here, succinate. Succinate, that's easy. It's become adding something back. Okay, so CH2, CH2, and COOH. Okay, succinate go fumarate. What you gonna have? Okay, here, what happens? Something special. FAD reduced to FADH2. These protons gonna gone. So what is structure formula? Whenever you see double bonds at the middle, they are not stable. Even in the food products process, double bonds is not stable. They always try to put something back. What are they gonna do? Add water. So, if you add water here, what will become molecule? This is malate. Okay, where is malate? In your beers, there's a malic acid. That's where the malate comes from. Okay, oxaloacetate. This guy is also magic. Same as alpha ketoglutarate. This happens, NAD reduced to NADH2. Okay, now, once this happens, these guys right here gonna go. So what's gonna happen? Okay, then they combine these, become citric acid, and they do the cycle. That's why this is called a citric acid cycle. Okay. What we missing? We missed something here. Alpha ketoglutarate goes here. You have another NAD reduced to NADH2. If we remember. Okay, we may forgot. That's okay. You're not going to remember everything. So that's why we forgot. And I said about energy currency. We have ATP. But don't forget the GTP, CTP, UTP can be used as a backup. Here, GDP will become GTP. So have another one here. This is same as ATP. And don't forget the transition step. There is another NAD plus reduced to NADH2. Okay, so let's do a calculation. 1, 2, 3, 4. Is that right? That is 3 ATPs multiplied by 4. Add, there is FAD become FADH2. Add 2 ATPs. And do not forget, there is another one right here. That is 1 ATPs. So the total is 15 ATPs. Remember, this is one circle. And you have 2 pyruvates comes out. So the total, you have to be multiplied by 2 equals 30 ATPs. Okay? Now, the question we just mentioned. How the bacteria generate ATP? Through NAD reduced to NADH2. How they going through FAD reduced to the FADH2? We go back here, okay? Reduced to NADH2. FAD reduced to FADH2. Now you know this is 3 ATPs. This is 2 ATPs. Now of course, some people say 2.5 ATPs. If they think about oxygen phosphate ratio, some people say this is 1.5 ATPs. That's okay. Then what's the mechanism behind this? The bacteria generate ATP. chemomotic series. And this process is oxidative phosphorylation. Okay? But then, how come bacteria create this GTP? How come the bacteria creates a GTP, ATP like here? And how they generate ATP like here? This is the one without electron transport chain. So we call substrate level phosphorylation. Okay, why we can do substrate level phosphorylation? Do you still remember we talked about 3-phosphoglycerate, phosphophenols, these chemicals has a potential to transfer phosphates. So those are strong phosphates transfer power chemical. And the ATP itself is too. The value of phosphophenols is like higher, it's like 69. The ATP itself is about like 40. Glucose 6-phosphates, fructose 6-phosphates, these are a little bit small. These are about like 17-ish or 13-ish. Okay, but they still can transfer and donate phosphates because those chemicals has phosphate transfer power capability. Okay, so that's the story. Okay, so we finished talking about here everything we concluded. Okay, very messy. Okay, so let's not talk about that complicated. This is for the people who want extra points. Is that right? How about the other people? Let's make it simple. I left it right here. These two can lock. So here we're gonna do some of the simple conclusion. We'll see what it looks like. Okay. So when we talk about from beginning to the end, like maybe you, what else biochemistry class we talked about just like 30 minutes. So that's too much. So let's do a little bit of conclusion. Okay, so let's do the calculation. So we talk about calculation of aerobic respiration. Okay, I just need it like this. Okay, what is that? We skip all the chemicals. Okay, you need to know. This glucose you still need to know. Goes here. Become pyruvate. Okay, pyruvate has a transition step. Become acetyl coenzyme A. Then have a cycle. Called the citric acid cycle. This is you need to know. Okay, this is about the key. That's as simple. We skip all the other chemicals. Okay, what I say is complete aerobic respiration, which means in the absence of oxygen. Which means the bacteria generate ATP will be going through chemosmotic and will be going through electron transport chain. Okay? So, during this 6-carbon area, we will use the 2 ATPs. We already showed you. This is 6-carbon. I said investments. Okay. This is 3-carbon area. The 3-carbon area, we created 3 ATPs, which is through NAD reduced to NADH2. That is going through ETC, electron transport chain. And we have 2 lines. So we multiply by 2, this equals 6 ATPs. Okay? But don't forget, we still have 2 substrate level phosphorylation happens. So that is 2 ATPs multiplied by 2, that equals 4 ATPs. So you add them together in the glycolysis stage, which is minus 2 ATPs, add 6 ATPs, add 4 ATPs. Now, do not forget, this is related to ETC. So this is coming through oxidative phosphorylation. This is no ETC, electron transport chain, involved. So this is going through substrate level phosphorylation. Okay, so add up together is minus 2 add 10 equals 8 ATPs. Okay, once you go here, let's just circle draw a little bit larger. Once you go here, you have to draw where the NADH is going to happen. Okay, this transition step, pyruvate become acetyl-CoA, which is NAD reduced to NADH2. This is 3 ATPs going to come out through electron transport chain, which is oxidative phosphorylation. Now here, you don't know chemicals. Let's say, I don't know, I don't want to know. Okay, I don't need those extra points. Then you need to know. Happened here, NAD reduced to NADH2. This is alpha ketoglutarate, goes here. NADH2 also happened, NAD reduced to NADH2. And it happened around here. This is FAD reduced to FADH2. And the final, oxaloacetate and malate right here, there's another NADH happens. And NADH2 happens. And don't forget, there is a substrate level phosphorylation. Right here is GDP, becomes GTP. Okay, then you add them. 3 ATP right here, 3 ATPs right here, 3 ATPs right here. And then one is 1 ATP right here, because GTP equals ATP. Then 2 ATPs right here. And this is also 3 ATPs. By the way, this is TCA cycle, okay? Citric acid cycle. Then you add them together. How many? This is 3 multiplied by 2 equals 6 ATPs. How about here? 1, 2, 3, 4, 5. So we do 3 ATPs multiplied by 3, add 2 ATPs, add 1. This is going to multiply by 2 also. Equals what? 24, is that right? Now,